Thank you, everyone, for joining this session. I'm very excited to talk about SGLang and Miles, two open source framework that we have spent time building on this that aim to help you build frontier AI infrastructure. And let's start with, what is SGLang? Some of you might already heard of and maybe are using it. It's an open source framework for inference and has been widely adopted in production, that people use it to serve open source models in many companies across all the categories. It targets for high performance inference that integrates all modalities into one engine. So we have the original main SGLang for LLMs, text models, LLMs, and vision language models. We have SGL diffusion for also the images, video generations, like VLA and world models. We have SGL Omni for audio models, like ASR and TTS, that's speech to text and text to speech. Also, it's well organized, optimized for agentic workloads. Also optimized, like AMD is one of the main silicons that's supported in SGLang and SGLang optimizes for. We also have wide day zero model support for all mainstream models, and also AMD is usually supported as on day zero of those models. And SGLang, more importantly, is always maintaining fully 100% open source. We also have Miles accompanied with that as an enterprise-grade reinforcement learning framework that basically, like people use SGLang to run models and run inference. Sometimes they also want to have a way to tune and train their model to be better at their workload, their specific workload, their specific use case. So Miles is a framework for you that you can run RL on some model. And basically, RL is a loop that between trainer and rollouts, that you have model and then you let the model run, like roll out that basically is the inference and it's run on SGLang. You got some outputs, and then those outputs you got reward on your outputs, and from the reward you can run backward and update ways through the trainer. Then you have a new model ways, and then you enter another round of rollouts again. So it's a loop that keep improving your models. And in this type of workload, rollout usually dominates 70% more RL GPU time. So like, while people might think inference RL are two things, but they actually are very highly correlated. Miles has also been used widely by different companies and widely personal users. It has been validated end-to-end on most of the mainstream models like DeepSeek V4 and Qwen 3.5, and also the GLM and Kimi series models. And it's run on ROCm today across MI 300, 350, 355, out of the box. So that's a high-level intro for the two frameworks. I want to also start from, like, before we dive into the technical deeper part, let me just show you an example of this AI field is growing fast. And this framework, like especially SGLang, has been developed for more than 2 years. But since new models keep coming out and new innovations coming out, framework development is something that, the most beautiful part is the optimization never end. And we'll keep working on both developing still fast. And this is example for DeepSeek V4. On day zero, on the first day, this is a model that cites 1.6T parameters. On the first day, AMD team and SGLang community has been able to make it runnable, and then soon, a few days later, we made it performant that can be run on production, achieved 500 tokens per second per GPU. Well, then after about just 10 weeks, the whole team keep improving it till about 4,000 tokens per GPUs, per second per GPUs. That's about an 8 times improvement. And the throughput performance number at that day actually is already comparable with B200. And if you consider the cost, the TCO, it's actually outperforming B200 in this case. So it's very impressive. But DeepSeek V4 is just one example. SGLang support is very widely across all the mainstream models, across like different frontier labs and all the modalities. So we have those, the first category, the LLMs, VLMs. We also have for efficient open models, and we have the diffusion category that including image and video generation. Another category not listed here is also like audio models, many of them. And they're runnable on AMD silicon. It's also adopted by widely by enterprise and rising star companies across all the categories, like hardware companies, hyperscalers, enterprises, all labs and products, developer tools, and neoclouds. And this only a small, very small set, selective small set of them. There's like hundreds of companies that we are keep talking with. And I mean, a lot of things are happening there, and people are building various features constantly. But we have 20 minutes. I'd like to give you something that can be impressive. So if we think about like one keyword this year, I mean, many keywords that's popular, like hot word this year, but agentic definitely one of them, I guess. So what's happening with agentic workloads also inspire how infrastructure design. And well, in the next few slides, let's go through some examples of how the workload changes affects the infrastructure design and developments. And the challenges around agentic is the workload becomes complicated. Well, it was complicated already, but now it's recently more demand and more complicated and more larger scale. So for inference, demand exploding, the workload is high that you need to run it with large-scale GPU deployments and with various tool calls and various environment execution things. And some of the challenges change and are unique because of the workload, that we need to optimize some new bottlenecks. And for training, agentic workloads makes the training become sensitive. And so all the details matters and must be done right and fast. So concretely, the challenges in agentic inference, I try to pick three of them, three prominent ones. The first thing is, because in agentic workload, you have multiple turns in one trajectory. So it makes your pattern highly repetitive. I mean, the prompt sent to the LLM is highly repetitive. So there are a lot of opportunities to reuse the cache. So high cache reuse becomes an important thing that the engine needs to catch. Cache hit rate becomes key. And we'll show in SGLang how we resolve that, what's the solution towards that challenge. And the second thing is model also becomes larger and larger. Now it's common for model to be 1 to 3 trillion parameters. And large model also changed the paradigm of how we run it with different parallelism strategies. And we'll see what the new thing that happened there. The third challenge is the context becomes long. That's similar, like accompanied with the first thing, because we have the long trajectory for agentic workload, the context growing, and usually 1 million becomes a common case. And the challenge then is how can we reuse do not avoid recomputing the preview, the prompt, and the chat history, the trajectory, and how we also run faster and still get efficient and low latency for the first token that's generating. So for this, the first challenge, we mentioned that because the workload becomes complicated, high cache reuse is important. While at the same time, because the model is large and the context is long, so people did many different innovations to reduce the attention computation complexity. There are many different attention variants. So the normal one is a full attention. Every token needs to look back at every token, so it's like n square complexity. And then nowadays, usually models are using not just a full attention layer, but they have mixed layers that contain full attention and also linear attention, and maybe also like window attention, many of them. And those different attention mechanisms require different design for the memory pool and the attention computation mechanism. Especially, it also affects how we manage the cache, Okay, maybe one background is in SGLang, in order to reuse the cache, we build the radix tree technique, which is a way for you to retrieve what is the prompt that has been processed before, so that you don't need to process it again. And now, because the different attention need different mechanisms, we upgraded it to be a unified radix tree. That's hybrid radix tree that can be one tree, but corresponding to different memory pool. So one tree solves all. That through this, you still can retrieve the KV cache, I mean the attentions you processed before, so that reuse it. And another thing is the context becomes super long. So cache hit rate important, but the GPU memory is still limited. It's not infinite. So it's important that we can cache as many tokens as possible. High cache is a technique according to solve that we utilize not only GPU HBM, but also to utilize host DR DRAM, and also external storage. There might be a remote storage, so that increase the cache hit rate a lot. And some numbers returned by our customers that we have experienced around Coin3 Coder in production, that cache hit rate, because of the high cache technique, increased from 40% to 80%, and TTFT got like more than half reduced, and we got 2 times higher throughput, things like that. And the second challenge we mentioned, like large model becomes huge, and that's usually they have huge MOE layer that they could have hundreds of experts, and then each time when the inference only activate a small set of them, a small set of the experts, and the whole model is too big for any single GPU or even single node, so that expert paradigm becomes an important technique, important parallelism strategy for running those large models. And the challenge here is you need to distribute the experts into multiple GPUs or even multiple nodes. And then a lot of communication happen. They need to translate the tokens, the data among those GPUs. And this, the trend started when DeepSeek V3 came out. It was about more than 1 year before. At that time, there wasn't a performant all-to-all kernel, communication kernel in open source world at least. But expert paradigm becomes important, so people started to develop performant all-to-all kernels. And we can see that AMD also reacted to that. Mori is a library that developed on top of DeepSeek Deep EP, that is a kernel library that specifically designed for AMD hardware that can run all-to-all kernels very fast. And with Mori library, then SGLang's been able to run expert paradigm efficiently on AMD GPUs. And also with some quantization, we can see the performance improved by more than 2.5 times compared to BF16 for the MX EP4 models on AMD. The third challenge, long context, we mentioned the context becomes 1 million is common. And there are several techniques corresponding to solving that issue. First example is we got chunked pipeline parallelism. It's a common technique, but it's a way that you store different layers of your network, your AM, into different GPUs, and then the pipeline to process different micro batches. The first worker process the first micro batch, while the second worker might process the second micro batch, so that you got a way of parallelism. At the same time, you also chunk the prefill into multiple chunks, so they process multiple different chunks at the same time. You reduce the latency of running the prefill for the whole input. Context parallelism is a similar parallelism for that. You still separate your input into multiple chunks into different GPUs, but they hold the same layer. The difference of these two is chunked pipeline parallelism gives you less communication overhead, but you might have bubbles if they are not balanced well. Context parallelism, you don't have the imbalance issue, but you might invoke more communication overhead. And high sparse is another category that we mentioned before. People are inventing different attention mechanisms. And one stream of that is sparse attention. And high sparse is a way that sparse attention is when a token look back to the history tokens, they only pick a small set of the history tokens to look at. So that inference only happen with a small set of the tokens. Well, the whole KV cache for all the tokens still need to be stored. So the optimization here is we store the whole the KV cache in CPU, the DRAM, rather than GPU HBM, while we only maintain a hot small buffer for the heavily heated tokens in GPU so that you retrieve it fast. And that's a way to increase, to make our memory usage more efficient so that we can enable a larger batch size. That's increased the throughput for sparse attention on long context by 5 times in our benchmark. And those are 3 examples for in inference. Well, the challenges in agentic training is actually similar. Like we said, the agentic workload makes the workload very complex. So you have the long context, you have the multi-turns, and you have many tool calls. The environment also diverse. That you might need to call another model. You might need to call an API, web API. You might need to run a code actually like in a sandboxing. So to handle diverse environments is one challenge in RL. And another thing is, we mentioned before, the agentic workload makes the training very sensitive. So training inference mismatch, training inference numerical accuracy becomes important. And if they are mismatched, that silently turns RL from on policy to off policy that can affect the RL effectiveness. The third challenge is although the workload is complex and the scale is large, but we still need to maximize the throughput while improving the policy. That's a forever topic. And we can, the first challenge is to handle diverse environments and tool costs. The way in Miles is we have broad integration with many different external tools, including Harbor, OpenInf, Prime Intellect Verify, and Daytona. So we have broad coverage for different RL environments that you can use Miles that are compatible for many different workloads to train your model. And to solve the second challenge, correctness thing, as we mentioned, like training inference mismatch it could be an issue, especially RL, you theoretically want it to be on policy that the training happens, the training weight updates happens after the full rollout. But for efficiency issue, people usually turn that into off policy that you don't always strictly align with update time. So, but still, the mismatch of that cycle and the mismatch of the training inference engine numerics, when the two mismatch mixed, things will be hard to debug. So training inference mismatch becomes an important thing that we want to make sure whatever the schedule is, your training engine forward always align with the inference engine forward. And to solve those consistency issue, several techniques we have developed in Miles, like for example, deterministic kernels in inference engine, and then we also match the kernels in inference engine and the trainer, so that achieves 0 KL divergence for inference and train engines. And token in, token out is another technique to align the chat template. There's many corner cases that people haven't been very carefully handled. And third thing, RL, which are like the rollout replay, that makes sure the experts selected during inference are the same experts selected during the training step, so that the training inference output goes through the same trajectory. That also lowers the probability mismatches. And with all those features, we also have day 0 verified training runs. Inkling is the most recent open source model that we worked with. Day 0 support in Miles for RL becomes a common thing for us now. Most of the recent models we have, you can used Miles to train them since the first day they released. And third topic is what we mentioned, which will be the forever topic that always we want high throughput. So makes your GPU more utilized, makes your job run faster. As mentioned before, the own policy RL training is that you have the trainer, you have the inference. This is a very high level illustration. I mean, a lot of things happening behind this. But conceptually, synchronous is that you run roll out and then you got reward, and then you train. You roll out again and got reward and train again. They are not overlapped, so a lot of idles on the both sides. And fully async is a common technique people use to resolve that issue, that you sacrifice a bit on the policy part, but you have a way to keep both the trainer and roll-out engines busy. So roll-out engine run inference all the time, and trainers run training all the time. That helps improve the system utilization and throughput, high throughput. At the same time, another thing the community developed on, that is low precision training. It's also very important now because that can accelerate the training and inference by multiple times sometimes. 8-bit and 4-bit quantization are some techniques we developed recently with HumanSync. Okay, so those are a few examples that we showed how the workload changes and the trends, new trends in AI, the whole AI industry, affect system development. But actually, a lot of things happen behind. SGLang has been developed for more than 2 years, and those are still a small set of features that we developed over the time. The first thing we started from RadixArk attention, that's already designed for agentic workload, and then more on zero overlap, a zero overhead scheduler. That's for reducing the CPU overhead, and speculative decoding, large EP, PD integration, and some of the parallelism strategies, and some of the memory management strategies, and some of the attention optimizations. Until most recently, DSpark, we see an interesting loop that speculative decoding got another round of innovation. And things never end. This is a picture for SGLang is still under fast development. At the same time, on the RL side, Miles, we recently also getting more and more users, and we focused a lot on scaling RL up to, more, maybe 10K GPUs, 100K GPUs someday. But before the end of the talk, also want to talk about the AMD ecosystem collaboration that we have had. We talked about SGLang on AMD, and SGLang has been working with AMD team for a long time. It's run on AMD out of the box. At the same time, the whole ecosystem, we work on things relevant around the whole workload. Like Miles, we already said RL, we can run Miles on AMD, so we easily got RL on Instinct out of the box. We brought the SGLang team's RL post-training stack to ROCOM, Nextron and FSDP backends. That's for RL, and SGL diffusion. We also show that can be run on AMD for image generation, and it achieves 1.5 to 6.3 times faster than alternatives. For the category of new clouds, we are working with DigitalOcean, and we achieved 3.5K tokens per second per GPU in production, and we proved that SGLang at production scaled on DigitalOcean MI355 GPU droplets. And with model companies, Zephyr is a good example that their model train on AMD GPUs and then serve SGLang working with them on their open source models using AMD GPUs. More examples, there are more examples that can run, that we showed that AMD GPUs can be used for both inference and RL training. And we have another training session workshop for Miles that you're welcome to join. We have SGLang booth over there. We have another talk on Miles that you can learn more on the details and technical side of how it works. In general, the mission of RadixArk, we are a startup we launched last year, and we center around SGLang and Miles currently, the two open source. And the whole mission for RadixArk is we want to make frontier-level AI infrastructure open and accessible to everyone. So currently, I mean, there are many frontier labs that they train the best model they're chasing for the frontier. But our dream is we want to say infrastructure shouldn't be something that hidden in those small set of labs, but it should be accessible by everyone. So everyone everywhere should have the chance to try your idea and run experiments and push in the frontier as you can. And open and accessible is the keywords and the thing we want to chasing in the future, including a better stability, usability, scalability, observability, and definitely performance forever. And thank you for the talk, and welcome to SGLang Miles family. You can scan the QR code to join.